In the evolution of life, the amphibians were doing a great job. They had colonized the land, but they could not move too far away from water because their eggs still needed water. In this lecture, we're going to look at amniotes and how they managed to take over the planet. We're also going to look at ecology and how the evolution of organisms changes the world. Be able to define adaptive radiation, extinction, amniotic egg, reptile, dinosaur, endothermic, ectothermic, bird, mammal, monotreme, marsupial, eutherian, and hominin. Label the parts of an amniotic egg and list clades of amniotes, identifying characteristics of each and being able to identify examples. The amphibians were doing quite well until everything went wrong. The end of the Permian was characterized by a mass extinction event. There was a lot of volcanic activity, gases in the air. 90% of life was wiped out. And this left a megacontinent, the supercontinent Pangaea. Unfortunately, the supercontinent Pangaea was very dry, which was hard for amphibians to live on because, of course, they need to retain water and live near the water. So this opened up a niche for organisms that could move away from the water. And one thing that allowed them to do that was the amniotic egg. The amniotic egg has evolved to survive away from water. It is a self-sustaining system. You have different parts of it, and let's take a look at its anatomy. The allantoid is the part of the amniotic egg that allows the disposal of wastes. This means that wastes do not need to go from the developing embryo out into the environment, but can stay within the shell. The amnion is a fluid-filled cavity, and that protects from external shock. So although you can crack an egg when you drop it, the amnion will help prevent any other shocks. And do remember that these first amniotic eggs were leathery rather than that hard shell you're used to cracking in the morning. The chorion allows for gas exchange, which is critical when you're surrounded by a hard shell. A yolk sac provides nutrients, although there are also some nutrients in the amnion. These were adaptive because they allowed organisms to lay their eggs on the land, and they would not dry out. And during the Permian, which was a very dry period, we're going to see that this was wonderful. You may also remember that the gymnosperms evolved during the Permian and that they have evolved to retain water well. And we're going to look at one group of organisms, the reptiles. These were the first organisms to have these amniotic eggs, and they, of course, also have very dry skin and a terrestrial lifestyle. Let's take a look at these reptiles. They have scaly skin to prevent desiccation, so preventing drying out has been adaptive for both plants and animals here. Later, things that were developed from the reptiles would have feathers and hair to prevent drying out. Some reptiles shed their skin. Remember, the ecdysozoans would grow to a certain size, then they would shed their outer skin and develop a new skin. Same is true with the reptiles. Reptiles have both ectotherms and endotherms. And you may be thinking, wait, aren't all reptiles cold-blooded? Remember that the clade reptiles includes things that have evolved from them later on, like mammals and birds. Reptiles have internal fertilization. Although frogs may go down to the pool to lay their eggs and lay their sperm and hope that those meet within the water, that doesn't work if you're far away from water. So internal fertilization is an additional adaptation to a terrestrial lifestyle. They also have rib cage ventilation. Amphibians will actually swallow air, and that's called positive pressure breathing. We're going to look later at negative pressure breathing, which is when the organism sucks the air into their lungs. That started off with the reptiles. And one group that did very well were the dinosaurs. Reptiles are able to crawl around on land. Think about how turtles and lizards move around the land, and you realize it's kind of this squamulose movement of crawling almost. Well, one group of reptiles developed different hips, and those would give rise to the dinosaurs. This allowed for increased speed and efficiency of motion, making them much more efficient predators and much more efficient foragers. So we see diverse groups pretty early on, including the ornithischian, which are the bird-hipped dinosaurs, and the saurischian, or lizard-hipped dinosaurs. Both of these were able to walk on 2 or 4 legs and were more efficient at walking on land, thus giving them an advantage over the reptiles. And you can see here one of the ways to use the advantage is to capture and eat reptiles. Many different clades arose as new niches were opened. Remember that most organisms went extinct at the end of the Permian. And during the Triassic, we start to see the evolution of dinosaurs into many of these new niches on land. And of course, new niches can create additional new niches. When there are megafaunal herbivores, that means something can evolve that can eat these megafaunal herbivores. Clearly, a lizard is not going to prey upon a sauropsid. So you have to have something that can eat these. And we're going to see early on in the Triassic that there were dinosaurs and there were crocodiles both exploring the land. And well, dinosaurs had a faster metabolism and had better hips, so they were able to move faster than crocodiles and forage better than crocodiles. So in the Triassic, the dinosaurs evolved better than the crocodiles and would evolve into new niches. We don't see crocodile herbivores evolve, we see dinosaur herbivores evolve. And we do see very large crocodiles, but we don't see large crocodiles persisting into the Jurassic later on. And there was this adaptive radiation. So what's an adaptive radiation? It's when a new niche is opened, in this case, movement on land efficiently using these hips, and that allows a lot of different organisms to take over a lot of sub-niches. So the adaptive radiation is when you have a lot of organisms evolving in a relatively brief time. So we saw that before when we saw the Cambrian explosion, and we're seeing it again here in the adaptive radiation of the dinosaurs. These were large land-dwelling organisms, and although there are large ocean-dwelling organisms such as sharks, these were on the land, and that was an open niche to just be big. There were also Mesozoic reptiles. These are not dinosaurs, but air-breathing aquatic animals. The reptiles returned to the ocean, and they evolved new types of limbs and tail for aquatic propulsion. You see this Kronosaurus, which was able to use all four of its limbs and its tail to move forward. And that has not actually happened since. We do not have any four-limbed movement in the water. And this Kronosaur was the apex of the food pyramid. It was about the size of an orca. So these organisms grew to pretty good sizes in the ocean. And dinosaurs were living in a wonderful utopia until the asteroid hit. As we know, about 66 to 65 million years ago, a large asteroid hit around the Yucatan Peninsula of Mexico and sparked massive global fires. Basically, it was like broiling the earth with the heat given off. And while there's a lot more to be said on that, we're going to keep it simple. Smoke and debris covered the skies for years afterwards, reducing global photosynthesis to an absolute minimum, causing the collapse of the food pyramid. The higher trophic levels, which require more nutrients, simply went extinct, meaning extinction, a whole clade has no living members. There are no more sauropods on the earth. They didn't have enough food, they went extinct. All the larger herbivores going extinct meant that larger predators went extinct as well. There are almost no theropods. There are no tyrannosaurids, for example. So all of these clades have no living members anymore, no pterosaurs. The crocodilians got a kind of last laugh. Because of their slower metabolism, they couldn't compete with dinosaurs in the Triassic, but because of their slower metabolism, they survived the Cretaceous extinction event. Birds also survived the Cretaceous extinction event. What is it about birds that makes them survive? Well, we know, just like dinosaurs and reptiles, they were highly efficient in water conservation using excretion through uric acid. Unlike reptiles, they were endothermic and thus able to provide themselves with the heat during this very cold period. That's right, after all the heat of the extinction event, it got cold when the smoke covered the earth. They are toothless, they can fly, and they have a high metabolism. These became more useful later on, but basically they were scavengers in a time when there was plenty of death going around. Mammals also survived. What makes mammals so special? They produce milk from modified sweat glands. They are very efficient at retaining heat, which is useful with these endothermic organisms. They have hair and a fat layer underneath the skin, being two layers of insulation, and could thus survive the very cold times after the extinction. Mammals have a highly efficient kidney and are very good at retaining water, and often, but not always, they have increased parental care, thus ensuring the care of their offspring. Some ways they care for their offspring are, well, We have amniotic eggs in the monotremes. These are the first mammals to evolve, probably in the Triassic or so. We have the marsupials, which have a pouch that can keep their offspring in. And we have the eutherians, which are placental animals that are able to care for their offspring until birth, which is an extended period of internal development. After the extinction, there were plenty of empty niches. Everything the dinosaurs could do was now an open niche. This allowed the birds and mammals to expand in these niches. The survival in the cold weather, drought, and scant resources favored some mammals and favored the birds after the extinction event. Biogeography, this interesting thing, kept the marsupials around only in Australia and South America, and the monotremes limited only to Australia. That's because of how the continents were at that point. Later on, the primates evolved, and we're going to take a moment to kind of look at these guys. What makes them so special? Well, they have opposable thumbs, they have binocular vision, and a large brain. Not only that, they have an even more extended care of offspring, allowing for greater survival, extended even to the point of sending their offspring to college to go and learn a whole bunch. Last, let's look at how evolution changes ecology. We talked earlier about the sponges and how sponges change the oceans. This was when you had suspension feeders, and these changed the oxygen content in the water by actually cleaning out a lot of the water. You have earlier, before the origin of suspension feeders, this murky, poorly mixed, low oxygen water filled with cyanobacteria, or as suspension feeders call it, food. And when they cleaned that out, that allowed more oxygen, causing more eukaryotes to thrive and grow larger. It is because of sponges and clams that we can have fish. Fish couldn't survive in the ocean before sponges and clams kind of cleaned it up. We can see this now, how herbivores and lignin-digesting fungi convert cellulose to CO2 and convert lignin to carbon dioxide and free up other nutrients. So we see how fungi will change an ecosystem. We can see how herbivores change an ecosystem. Here's an example where we've caged a certain amount of the land away from herbivores, and you can see how it is very different looking than the land eaten by the herbivores. Predators control herbivore populations and allow the land to stay greener, so the evolution of predators will actually change the amount of greenery around. Remember that biomes are determined by plants and their herbivore interactions. A lot of organisms evolve due to the evolution of new niches. Think about how fruit probably first evolved to be distributed by, well, fruit-eating animals, which at the time were probably dinosaurs.